In this video, I want to show how to solve the coupled Cahn-Hilliard equations in 2 dimensions using Julia. Now, I have already a code to solve this problem in Python, so I am just going to translate the code into Julia, and this is quite easy to do. So before doing that, I just want to show how the code works. This is a phase separation. This is order parameter u, order parameter v. We can see there are 3 layers in this particle. We can have a particle with less layers if we change this parameter here from 50 to 0. I'm going to run it one more time. Now we have a particle with 2 layers. This is a Janus particle. Alright, so to translate this into Julia is quite simple. I'm just going to start with these parameters. I'm just going to copy them there. The next thing to do is to build a function to initialize the system, initialize conditions. So let's see a function initialize arrays, and this is going to be a function of let's use the number of nodes. So we are using here the length. Now I'm going to use number of nodes. I think this should be 50. I'm going to turn on my Julia. So the length divided by the spacing is 0.8 by 0.016. This is 50. So I'm going to use the number of nodes instead of the length. And this is going to be also a function of, so we have here a random uniform distribution. I'm going to take some amplitude of this distribution. I'm going to call it noise. And then also we need a value as the center of the distribution. So this value is going to be u0 for u, let's see, for instance 0, and v0 for v, which is also 0.0, and the noise some values, 0.4 for instance. Okay, so what we have inside the function is the random distribution n by n. I'm going to multiply by some amplitude, and then I'm going to move this distribution about some value. Now one thing here is that, this is a matrix n by n, and this is a constant. So to do this element wise, we need to use a dot there. And this is going to be what I return from the function. Okay. And then I can call this function somewhere for the value of u. And the same for the value of b. The difference is going to be the center of the distribution. So this is u0, and this is b0, and the noise. Okay, I think that's it. What else we need here? What else we need? Let me see. Yes, we need to visualize the result. So in Julia, I'm going to use a heat map. So I'm going to build a function to visualize the arrays. I'm going to call one U and then B, and these are going to be heat maps. Heat map for U and one more heat map for V. That's it, and then I'm going to plot these heat maps. Let's call this one B1, B2, and then I plot both P1 and P2. So to plot this I need some layout. I'm going to plot one row, two columns. What else? Some size. This is in pixels. So let's do 800, 400. What else? I think that's it. And then we display the plot. So this plot is an object. Okay. Object 1. Okay. So I'm going to display this object here. I think that's it. What else? So I need that's it. I'm going to put this calling to the functions inside a main function. And then we are going to call this visualization function. Okay. I'm going to put these constants inside the main. So looks like it's done. Let's see. I can just try to run this to see if it works. It takes a little bit longer time than Python. Just the first time we compile this. After the first time it is faster. So it didn't do anything, I think because I didn't call the main function. Let's call it and run it again. Yeah, it works. So this is the distribution for U and for V. So we can see here that the values of they are all positive. So I need to move the center of the distribution. For U, I'm going to move it a little bit to the left. The reason for this is because in my experience, to build a copolymer particle, we need more homopolymer than copolymer. So we have to move the distribution of the homopolymer a little bit to the left to have more homopolymer. So I'm going to run it again. Yes, now we have this distribution is a little bit more to the left, to the negative side, and this one is too positive. I want this to be the opposite. We want a symmetrical polymer, so we need to move this distribution also a little bit to the left, not too much. Let's see if this is enough. Yeah, now it's symmetrical. I'm going also to change the color to be able to distinguish the distributions. Color, and the other is a different color. And I am also going to change the aspect ratio. The same for this. And run it again. Now it works. So this is a little bit negative as I want my distribution, initial distribution for U, and this is my distribution for B, which is more or less symmetrical. Alright, so the next thing to do is to advance this initial distribution. So in Python, the way I did this part is with this function here, solved_pd. So I'm just going to copy. Wait 1 second. Now this. Okay, let's until here. Okay, let's copy this part somewhere, for instance there. Okay, so now I just need to change a little bit the syntaxes of this function. So this, let's call it function. Okay, I don't need these dots here. I need to close the function at the end. Okay. I need also to close this loop. And now I change the syntaxes. So this matrix product is like this. There is one more somewhere. This eyes, I'm going to replace that with an eye. And what else? Let me check where this function ends. This function ends here and then return. Yeah, it's okay. I don't know why there is an error there. Okay, let's first finish whatever I can do first. So for this I need ITT in 1, 2 steps. And what else I need here? Okay, this one. I need to use this hat for the power. And another thing very important is that these powers are element wise. So I need to use the dot. There is is another matrix multiplication there. So instead of this add, I'm going to use a star. Okay, one more here. And there is another matrix multiplication there. No, this is not matrix multiplication. This is a element-wise multiplication. So I need to use a dot. That's it. Looks now correct. Okay, convert M1 and M2 to CS format. This is sparse format. So this is going to be sparse. 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 And to handle this sparse matrix, I need to use a new library using sparse arrays. And this is also important. So this is the solution of the linear problem. So what we have here is m1u equal to bb1. To solve this in Julia is very similar to the way it's done in MATLAB with a backslash. So use a backslash in both sides for u and for b, and I don't need these parentheses any longer. Just remove them. So this operation, for doing this operation, we need another library for linear algebra. Linear algebra. Okay, so that's it. I don't need this flag here. Yeah, I think that's it. Okay, so I'm just going to call this function in the main. Copy this here, initialize, and then, but there is another thing we have to do. We need to resize, because these are n by n arrays, and this function takes column vectors, so we need to resize. I'm going to make a column vector for you. You call equal to resize. Resize what? Resize u into a column vector, and the same goes for b. Resize b into a column vector. So the initial condition created here is resized into a column vector, and this is what is going to take this function here to solve the problem. This is for you, and the same with, I'm going to type it better. You call, and this is going to be call. Correct? Yes. So this is capital N, then n steps. This is dt. Epsilon u. This is epsilon b. Sigma. Then a. Then b1. b2. Tau b. Tau b is right there. Okay, this should be capital 1, and capital B, B2. Now we need also this Laplacian here. So there is a problem. Well, not a problem, but there is an issue with the Laplacian. The Laplacian in Python is defined like that. So what I do here is create a Laplacian in one dimension and then use Kronecker product to build the Laplacian in two dimensions. So at the moment I don't know how to build the Laplacian in two dimensions using Kronecker products. So what I'm going to do is just write the Laplacian in two dimensions in Julia from scratch. And I have that function already from a different code, so I'm just going to reuse it. I'm going to put it somewhere, for instance here. And so what this does, this function is build a Laplacian in two dimensions with periodic boundary conditions. That's what it does. So it takes as arguments the number of nodes, the separation between nodes, and then I'm going to call this function before solving the problem. So it should be here. This is going to produce the Laplacian in two dimensions with periodic boundary conditions, and I'm going to use this Laplacian here as the argument to solve the problem. So let's just run this thing to see how it works. Let's see if there is no mistake. There is an error. Let's see, resize not defined. Resize not defined. What happens there? Maybe it's not resize, maybe it's reshape. Reshape, yes, reshape. Reshape. Okay. Let's run it. There is another error. Oh, SPU not defined. So in Julia, this LU factorization is written like that. Okay, so one more time. Okay. This is the initial distribution, and there is another mistake. No? Visualize. Ah, I see. I solved the problem, the solve PDE, but I didn't wrote the solution. UV equal to this. Okay, run one more time. There's nothing. Let me see what is the problem now. Let me check the code. I think there is another thing here. We need to reshape one more time before visualizing, because these results here are column vectors. So we need to visualize the solution. We need to reshape the solution into n by n. So u equal to reshape u n by n, and the same goes for b. Reshape b n by n. Run it one more time. Let's see. Now it works. See, we have here a Janus particle. So remember, these are periodic boundary conditions. So I can try to use a different initial condition to see if it changes the location. Let's see. Yeah, I think this one is better. So here we have a Janus particle, two dimensions. and the distribution is correct. Yes, so we have here more or less symmetrical distribution for order parameter b, and this is the order parameter u, and it looks correct to me. So I'm going to check if this works for a higher value of the sigma. Let's see, sigma equal to 50 now should have more layers. Yes, so now we have here a particle with 3 layers. Okay, so with this I conclude the explanation of how to rewrite a code from Python to Julia to solve the couple Cahn-Hilliard equations in 2 dimensions.